Okay, so this example 6 here, let's kind of analyze what we got here. First of all, I see two polynomials multiplied together, right? I see 2x plus 1 to the fifth times x to the third minus x plus 1 to the fourth power. So what does that tell me that I have to do? If I see two things multiplied together? The product rule. Ooh. Now, within each one of those products, I'm going to have to differentiate these pieces. When I go to differentiate this, what am I going to have to use? The chain rule, because it's a function within a function, right? When I go to differentiate this, what am I going to have to use? A chain rule. So this is actually a product rule with two chain rules in it. Okay? Oh, this is going to be fun. What a fun Friday. Let's go. I'm so excited. All right, now understand that there is a different option. Okay, there is a different option. I would strongly encourage you not to take this option. However, could we take 2x plus 1 to the fifth power and multiply it all the way out? Sure. Could we take x to the third minus x plus 1 and multiply it all the way out to the fourth power? Sure. And then multiply all of those two giant polynomials together? Yeah. But then in the end, the differentiation would be a lot easier, right? Because then it would just be one big long polynomial, differentiate it all really easy. Knock it down, bring it in front, knock it down, bring it in front, knock it down, and so on. Okay? Now, the differentiation, finding the derivative is a lot easy, or is a lot more difficult, but in the end, the simplification is a lot easier. Okay? 6 of 1, half dozen of the other. All right, so remember, the product rule is f prime g plus g prime f, right? So let's find f prime. Let's find f prime. Now, when I go to find f prime, I have to use the chain rule. So I bring it out front. I leave the inside the same. I knock it down 1, right? Remember, chain rule says derivative of the outer times the derivative of the inner. Okay, the outer is the fifth power, right? That's the outer piece of this. So bring it out front, knock it down 1, times the derivative of the inner. Well, what is the derivative of 2x plus 1? Just 2. Okay, now the end of the product rule says times g. X to the third minus x plus 1 to the fourth power. Plus g prime f. Now g prime, bring it around front, 4, x to the third minus x plus 1 to the third. And now we multiply it by the derivative of the inner. What is the derivative of the inner? 3x squared minus 1. Good. Times f. Now, I want to see how far I go with the simplification. I want to see what I did, what the book does with the simplification. Oh, I'm sorry. Thank you. Okay. There's just a couple things that we could do. We could take the 5 and the 2 and multiply it together to make a 10. And we got 2x plus 1 to the fourth, x to the third minus x plus 1 to the fourth. And then take, there's nothing to multiply. This just stays the same. 4, and then we'll put the because this came first over here, 2x plus 1 to the fifth, and then we'll put the x to the third minus x plus 1 to the third, and then we'll tack on this 3x squared minus 1 at the end. Now, there's one other thing I could do to kind of simplify it. Kind of. Do you see how there's some like terms in here? Like I have in these two big chunks, I have some like pieces. So I'm going to just kind of factor those out. First off, what's the GCF of my numbers? 10 and 4. 2. So let's pull out a 2. Okay. Pull out a 2. And then let's pull out as many 2x plus 1s as we can. Okay, well, I've got a 2x plus 1 to the fourth, right? And then pull out as many x to the third minus x plus 1s as we can. So it looks like I can pull out 3 of them. And they don't share a 3x squared minus 1 in common. So we're just going to leave that. So now that's going to get me all multiplied by. So 10 divided by 2 is a 5. And then here I pulled out all 4 of the 2x plus 1s, but still left over an x to the third minus x plus 1 plus. Okay, now I pulled out 4 of my 5 2x plus 1s. Oh, I'm sorry, 4 divided by 2 is a 2. Here. I pulled out 4 out of my 5 2x plus 1, so there's just still 1 left over. That's a 2x plus 1 there. Oh, geez, made it look worse. 2x plus 1. And then I pulled out all 3 of my x to the third minus x plus 1. But left in there, my 3x squared minus 1. So you know what I'm going to do? I'm going to try to simplify this a little bit more. I'm going to keep going inside there. 2x plus 1 to the fourth, x to the third minus x plus 1 to the third. So this is going to be 5x to the third minus 5x plus 5 plus, now when I go to FOIL this, first is 6x to the third. Inner is plus 3x squared. Outer is minus 2x and then minus 1. So when I go to multiply all of that by 2, I get 12x to the third plus 6x squared minus 4x minus 2. So I can combine like terms in the middle there. Or combine like terms on the far right side. So 2x plus 1 to the fourth, x to the third minus x plus 1 to the third. And now what is this going to give me? This is going to give me 17 x to the thirds, 6x squareds, a minus 9x, and then a plus 3. And I think that's as far as we can go without taking powers. I could try to factor that down and see if that would do anything, but that's not going to do anything. Spoiler alert, that's not going to factor. Especially because we got a 17 out front. That's not going to do anything. Okay, questions on that one? Okay. I'm clearing from this page. Let's take a look at this next one. Differentiate y is equal to e times e to the sine of x. This one requires a lot less work. Now, do you see how I have to use the chain rule? Okay, do you see how I have to use the chain rule? I've got sine of x within e to the x, right? Within e to the something. So I've got two functions going on. I've got the e and then the sine x. Now, when I go to differentiate, I go outside in. So what's outside in this? Well, outside, I can't break into the exponent until I deal with the base. So my f is really e, and my g is sine x. Okay? Because it's f prime g of x times g prime x, right? That's chain rule. F prime of g of x, f prime of g of x times g prime x. That's what I'm referring to with my f and my g. All right, so now when I take f prime, what is the derivative of e to the something? E to that something, right? Derivative of e to the x is e to the x. So when I take y prime, my f prime g of x, this first chunk is just the exact same thing that I see there. E to the sine x. But now, because of chain rule, I have to not only just say e to the sine x, what do I have to multiply it by? What am I going to multiply by? Times the derivative of this. What is the derivative of sine? Cosine. And that's all I can do with that one. E to the sine x times cosine x. Yeah.
I thought the f was always on the outside.
Yes, f is on the outside. G is the inner. You see how it's in the exponent?
Yeah.
So g is the inner. Sine x is the inner. Okay, the outer is technically f. E. Here. Okay, e to the x is technically my innermost, or my outermost function.
Is there any reason why that they're flipped this time?
Because if I go to evaluate something, I plug in a number for x. What are you going to do first?
On the sine of x.
Which means that's the innermost function.
Okay.
Okay, now, you know what we haven't found the derivative of yet? We have not found the derivative of, okay, what's the derivative of 2 to the x? Maybe instinctually we might say x times 2 to the x minus 1 or something like that. But that's not the case. We can't do that. We have not found the derivative of exponentials yet. You know what we actually have to do? We actually have to apply the chain rule to it. So I am actually, a lot of the rules, I just show you what they are and tell you got to memorize them. This one, I think we can follow along. So try to follow along with this rule. We can actually use the chain rule to evaluate any b to the x. So 2 to the x, 3 to the x, or whatever, 7 to the x, whatever, number to the x power. As long as we take this rule, and watch here, if I have b to the x, and again, b is just any number, okay, b to the x, and I say I change it into e to the ln of b. Now, that little piece in there, e to the ln of b. Remember our rule about that is if you have e to the log base e of b, that's ln, right? Those things will cancel and just leave me back b, right? That's what I'm doing here. I'm actually kind of manipulating. I'm going to change the way it looks a little bit so that I can differentiate it. I'm going to change b to the x into e to the ln of b, okay? Which is essentially just e to the ln of b times x. Now, when I go to differentiate that, all I'm doing is saying, okay, if these two things are equivalent, I'm plugging that in there. And let's see what I can do to differentiate it. Well, e to the ln of b to the x, that's a chain rule. E to the something, and then the ln of b to the x, or ln of b times x, that's chain rule. Those are two separate things happening at once, right? A function within another function. We just saw it here with the sine of x within the e to the x. Now, when I go to find the derivative of it, I am going to find, because I have to use chain rule, I'm going to find the derivative of e first. Well, we just saw that it's the exact same thing, right? The derivative of e to the ln of b to the x is e to the ln of b to the x times the derivative of the stuff up in the numerator, up in the exponent. So when I go to find the derivative of the stuff up in the exponent, guys, what is this? Isn't ln of b just a number in the end? If I say my base is 2, I would be just saying ln of 2. Isn't ln of 2 just a number? Just a value, just a constant? So what I can do here, since it's a constant, I can remove it out to the outside. I can say, well, then it's a b to the ln of b times the derivative of x. What is the derivative of x? 1. So it actually ends up being 1 times ln of b. Or, in our other words here, that'll cancel again, b to the x ln of b. B to the x ln of b. All of that just for the derivative of any exponential is itself times ln of b. The derivative of any exponential is itself times ln of b. And what is b? B is the base, whatever we choose it to be. No pun intended. So if I were to try to find the derivative of 2 to the x, well, then the derivative of 2 to the x would just be 2 to the x ln of 2. And remember, ln of 2 is just a constant, right? Just a number. The derivative of 3 to the x would just be 3 to the x ln of 3. Derivative of 7 to the x, 7 to the x ln of 7. Now, you may be thinking, well, wait a sec. We knew that e to the x was just e to the x. Does it follow the same rule? Well, e to the x ln of e. What is ln of e? What is log base e of e? 1. So this does follow the same path. That's just e to the x times 1, or just e to the x. Okay. So you may have thought maybe we're learning something different. No, it's the same type of thing. Just e to the x ln b. Okay, so that means let's you know what? Let's do this one first, and then we're going to jump back and hit example 8. Oh, maybe not. Is there another example in there? Oh no, this is right. This is right. I was just on my last page. Whoops. Oh, I don't even have to use that rule. Oh, that's a shame. I thought these problems had to use that VDX LNB. You'll probably have to use it in the homework. No problem. This one's good too. This is fun. This just has another chain rule in it. The reason why I don't have to use that fancy v to the x LNB is because there's a base e. Since there's a base e, then the derivative of the exponential e to the x is a lot easier. It's just e to the x. If this was like 2 to the secant 3 theta, should I change it into 2? No, that's okay. If this was like 2 to the secant of 3 theta, then I would have to be a little bit more fancy with it. I'd have to use that rule. But let's just do it as it sits right now. E to the secant 3 theta. Okay, this is actually a chain within a chain. Okay, this is a chain rule within another chain rule. Let me show you how. If I wanted to find the derivative of this, I have to start with my base, right? What is the derivative of the base? What is the derivative of e to the secant 3 theta? E to the secant of 3 theta. Ooh, green. Okay. Times the derivative of the stuff up in the exponent, right? Because that's the chain rule. I have to take the derivative of the outer times the derivative of the inner. Now, I have to find the derivative of secant 3 theta. Now, when I put a 3 theta on the inside, that actually makes it another chain rule. When I go to find the derivative of secant 3 theta, first of all, what is the derivative of secant? Anybody remember?
Secant x cotangent x.
Close. Secant x, tangent x. So the derivative of secant 3 theta is secant 3 theta times tangent 3 theta. Now, this is another chain rule because there was something within the parentheses. Well, there's no parentheses written, but there's something in there. There's something inside the secant. It's 3. See, if this had just said the secant of theta, then we'd be done. But because this says the secant of 3 theta, now I have to multiply again on what is the derivative of 3 theta? What is the derivative of 3 theta? 3. Right? So I have to multiply this by 3. And that's the tendency is to leave off that last step. Because it ends up looking like you're done, but since there is something else inside secant, you have to multiply by the derivative of that thing as well. And if it's 3 theta, it's just the derivative ends up being 3. It doesn't just go away. That would be like if it was the derivative of theta plus 3. Then that 3 would go away. But because it's the secant of 3 theta, I have to multiply 3 back on. So just to kind of reorder it a little bit, this is 3 times e to the secant of 3 theta times secant 3 theta times tangent of 3 theta. Now, I don't believe there's, 3 theta. I don't believe there's any trig identities that we can use. Hi. Thank you. Okay. Okay, one last problem. Now, this is a little bit more evident that this is a double chain rule. Chain within a chain. How do I see that? Well, I've got a trig within a trig within a trig, right? I see 3 things happening. So let's start with our outermost function. So what is the derivative of sine? Cosine. So this starts by taking the cosine of cosine tangent x. That's the derivative of sine. And then we multiply on the derivative of cosine. Well, what is the derivative of cosine? Negative sine tangent x. But we can't stop there because there was something within cosine. We have to keep multiplying on the derivatives of the insides. So what is the derivative of tangent now? The derivative of tangent is secant squared x. Secant squared x. And if there was something within tangent, I would have to multiply on the derivative of whatever's on the inside of tangent as well. Like say this was tangent of 5x, right? Sine, cosine, tangent 5x. Then I would have to multiply this whole thing by the derivative of 5x, which is 5. Okay. I don't think there's anything. Is there any simplification I can do there? I guess bring the negative all the way out front, but that doesn't really do anything anyway, does it? So I can leave it like that. That's just a demonstration of 2 chain rules at a time, a chain in a chain, right? Because here was my derivative of the sine. Here is my derivative of the cosine, and here is my derivative of the tangent. So you keep peeling back the layers, right? That's the way that my calc teacher always taught us. When you're doing a chain rule, you kind of like peel back the layers, and you keep multiplying on the derivative of the inside. The key thing here is to remember that you don't change the inside of the function when you find the derivative of the outside. Like for example, I don't do anything to cosine tangent. That stays when I find the derivative of sine. Just like this, I don't change tangent. I just find the derivative of cosine applied to tangent. I'll deal with tangent once I peel back the layer. So I peel back the layer. Okay, now I find the derivative of tangent. Okay. All right, I'll shut up now. I'll give you guys the rest of the 10 board. No, that's okay. That's fine.
Just so I don't know, Dave, you guys don't watch it.
Yeah.